Good evening, everyone. Welcome to Module 3, the core logic of Find My File app. Here we are going to discuss the on-device file processing in this session. In the last section, we saw how the UI is built. Now we are going to dive into the most critical part of the application architecture, the core logic that actually does the main work. This module is all about how we securely access, read, index user files without ever freezing the app. So we are going through the agenda. So let's go through the agenda of today's session. We will cover logic optimization or decongesting the main thread. Then we will discuss about secure file access. How did we enable us? The storage access framework for this application. Then we'll deep dive into the FileIndexerWorker.kt, which is the main file for the logic layer. Then we will do some kind of practice, a simple practice, to show how we can add support for .txt file. And then we will summarize and discuss about the next session. Before we look at our solution, we have to understand the number one enemy of a smooth Android application is doing the heavy work on the main thread itself. The main thread's only job should be to handle user input and draw the UI. If you ask it to do anything else, it will slow it down. Like reading a large file or running AI model, the entire app will freeze. This is what causes the dreaded application not responding or ANR error. So always keep that in mind. Our app's core task, indexing file, is incredibly heavy. Doing this on the main thread will make the application completely unusable for users and the focus will be lost. The solution is to move all of this work into the background to the logic layer instead of the UI layer or main thread. To solve this, we use Work Manager, which is Google's recommended library for guaranteed background work. When a user adds a folder, our main view model doesn't start indexing the files by itself. Instead, it creates a work request and hands it off to the Android operating system. The OS then schedules our file indexer worker to run in a separate managed background process. This ensures that even if the indexing takes a long time or the user closes the application, the work will still be completed and the main UI thread remains completely free and responsive. But how do we get access to the user's folder in the first place? Modern Android is very strict about privacy and they don't allow us to read any folder that we want. That is why the storage access framework has to be developed for this file, which is very different. We use the storage access framework or SAF, which when the user clicks to add a folder, we don't build our own file browser. Instead, we make a request to the Android system, which then opens the phone's built-in trusted file manager. The user navigates and selects a folder, and when they confirm, the system gives our application a special persistent permission grant to read the contents of only that specific folder. That's why we are able to secure, respect users' privacy, and this approach is the modern Google recommended way to handle file access for any application. This brings us to a crucial real-world challenge. You'll notice that the users cannot select top-level folders like the main download directly. This is intentional. It is part of a security model called scoped storage. Android prevents application from getting broad access to any shared storage. This is a strict privacy rule with them. An application cannot move files using programs or codes, and the typical user cannot create automated file moving rules on a standard Android phone. So, what is the solution? We cannot change the rule, so we must design a better user experience. We need to guide the users, explaining that for their privacy, they should select specific subfolders where they save their important documents. This turns a technical limitation into user-facing feature that highlights our commitment to security and user control. So if you look at the application itself, it gives you an option to select the files which the users can select, and the application will index and look through the files only for the selected folders. Okay, so let's do a deep dive into the FileIndexerWorker.kt. This is where everything happens. The do work function, if you can see, is the entry point. First, it gets the URI of the folder that the user has selected. It then uses the document file API, which is part of the storage access framework, to safely list all the items inside that folder. We then loop through every item. If it is a file, we begin the process of extracting its text content. This code, a file indexer worker, is the Android class that operates in the background to scan a specified folder on the user's device. The primary purpose is to extract text from various file types and save the text along with the file metadata into a local database for later searching. File indexer worker, the function, is a background worker designed to process and index files from specified folder. The do work is the main function that executes on the background thread to find, read, and save content from file. Get text from PDF is a helper function to extract all text content from PDF file. Similarly, get text from docx is a helper function that extracts all text content from Microsoft Word. Get text from XLSX is a helper function for Microsoft Excel. So if I have to do a core activities for do work, which is the main body of this code, first thing it does is receiving input and setup. The worker is initiated with a folder underscore URI as input. That's the object we have defined inside. It converts the URI into a format that allows it to access the files within the folder on the device. It also initializes a helper for text recognition from the images. Then second, it iterates through the files. The code gets a list of all files inside the specified folder. It then iterates through each one, checking if it is a file and not a folder before attempting to process it. Then third, content extraction is done. Based on the type of the file, and we have defined the helper functions, the worker uses different methods to extract its content. For example, images, it uses text recognizer helper to perform optical character recognition. This we had discussed in session 1 and session 2 as well, converting the text into image into a searchable string. Then we have PDFs. We use iText PDF library. Then docx and XLSX, we use Apache POI library. Then for other types, it skips the file, which is it image, PDF, docx, or XLSX. Then fourth, it does the data storage. For each file that it successfully processes, it creates a file entity object. This object contains important information like the file's URL, URI, name, folders URI, and the combined extracted text. The text content is combined with the file name to make both searchable. So it's ensuring that the content as well as the title is being searched. Then you have database insertion. After processing all the files in the folder, the worker uses a room, which is a persistent library for Android, to insert all the created file entity objects into a local database in a single transaction. This ensures efficient and atomic data storage. And then it also has code for error handling. The code includes multiple try-catch blocks to handle potential errors, such as a missing folder, unreadable files, or issues during text extraction. Logging of these errors to provide debugging information is also done. If a critical error occurs, the worker reports a result.failure to the system. So let's go into the on-device AI/ML kit for text recognition. For images, we use an on-device AI/ML model. Our text recognition helper class is a wrapper around Google's ML kit for text recognition. When the worker finds an image, it passes it to this helper. MLKit's pre-trained AI model then runs directly on user's phone to perform OCR, or optical character recognition, and extracts any text it finds in the image. The most important part is that it is 100% on device. No images are ever uploaded to a server. None of the data from your phone goes out of your phone to the internet or anywhere else. This is a critical feature for user privacy and a key selling point for this application. Now let's look at the final step of saving the output or these conversions to database. After the text has been extracted from any file, whether it's PDF, docx, or image, or XLS, the final step is to save it, and in a format which we can use later. For each file, we create a file entity object. This is our room database entity. We combine the file's title with its extracted content to make both of them searchable. To be efficient, we add all of these file entity object to a list. Then after the entire folder has been processed, we call our DAO's insert all function to save all the new records to the database in a single fast transaction. So if I have to simplify the code, the first one which you will see is val file entity equal to file entity. This line creates a new Kotlin object called file entity. Think of this object as a structured digital note card that holds all the important information about a single file that it has just processed. So its unique path, URI string, its name, the title, all the text that has been extracted from its content, and when was it last modified. So these information go into file entity object. The next important code is DAO.insert all file entities to insert. This is the command that actually saves the data. DAO is our data access object, which is part of the code that knows how to talk to the room database. Instead of saving each node card one by one, which can slow the application, we first gather all of them into a single list called file entities to insert. The insert all function then takes this entire list and saves all the records to the database in one single highly efficient batch operation. Okay, so at the end of this session, let's do a small project. Your task is to add support for basic.txt files. This is a common file type, and it's much simpler to process than the other file types. You have to open the FileIndexerWorker.kt file, find the when block that checks the file types, and a new case to handle MIME type of plain text, which is text/plain. Read the text inside this new case. You don't need a special library. You can read the content of the input stream directly into a string. A simple way to do this is input stream.bufferedReader.use it.read text. Assign the result to the recognized text variable. This lab will give you experience. Now you don't need to do all of that. Just 2 lines of code or 1 line of code, whichever you're comfortable with, you should do it. Okay, so here's the final code. So what the code does, in short, this code is a case within a when statement, similar to a switch in other language. It executes only when the file being processed is identified as a plain text. The job is to read all text from the file and store it in a recognized text variable. So step-by-step explanation of this code. The main line, recognized text equal to stream.bufferedReader.use. Stream, this is an input stream. Think of it as a raw one-way pipe of data or bytes flowing from the file. It is the most basic way to get data, but it is not very convenient for reading text directly. Buffered reader. This is an extension function that traps the stream in a buffered reader. This is done for 2 main reasons. One, efficiency. Instead of reading 1 byte at a time from the disk, a buffered reader reads a large chunk into memory. Reading from memory is much faster than reading from the disk repeatedly. So it's more like doing a batch processing. Convenience, it provides helpful methods specifically for reading characters and text like read text. Then .use, which you're seeing, this is a crucial Kotlin function for safely handling resources that need to be closed like file streams. The .use block automatically closes the stream once the code inside the curly braces is finished. Even if an error occurs, it will close the code. This is extremely important for preventing a resource leak that can crash your application. It's modern, safe alternative to a traditional try finally block. Last is it.read text. Inside the .use block, it's the default name for the object it's working on. In this case, the buffered reader. The .read text function does exactly what its name implies. It reads all the remaining text from the buffered reader from the current position to the end and returns it as a single string. So if I have to put it all together, the entire line executes as following. Takes the raw byte stream from the file, wrap it in an efficient text-aware buffered reader, executes a save, use block on that reader. Inside the block, read all the text into a single string. The use block automatically and safely closes the reader and the original string despite error or success. The resulting string is assigned to a recognized text variable to be used further. So before we wrap up, let's look at what we have done during session for module 3. In this model, we covered the workhorse of the application, the entire on-device file processing pipeline. Background processing, we learned why heavy tasks cause the application to freeze and ANRs are generated, and how we use Android's Work Manager to run our file indexing in a separate guaranteed background process. Second, we looked at secure file access. We explored how the app uses the Storage Access Framework, SAF, to let users securely grant access to specific folders. And we discussed the real world challenge of working with Android's scoped storage privacy rules. Then we looked at the file indexer worker. We did a deep dive into the worker's code to see how it lists files and uses a when block to handle different file types. Then we looked at third-party libraries, for example, iText PDF, Apache POI, and so on. And then we looked at on-device AI, what it does, the OCR, and finally we looked at the saving data code. So we've covered the final step of the processing, creating file entity object and saving them to the database in an efficient batch transaction. Next, let's look at the local database or the application's memory, the local room database that makes search possible or instant search possible. We will look at introduction to room. We'll cover the three main components of the room database: the entity, the data table, the DAO, the query interface, and the database class. We will look at full text search, FTS. We'll learn why a standard database query is not enough and how we use special FTS table to perform highly optimized searches for words inside large blocks of text. Then we'll look at the database schema. We'll do a walkthrough of our database files to understand how they are defined. We'll look at debugging with the database inspector. We'll learn how to use the powerful app inspection tool in the Android Studio to view the live content of our database while the application is running in the emulator. And then we'll do some practical lab. Thank you for joining. Let's see you in the next session.